Nothing big's happening. I'm just
Oh.
recording what happens on my computer for the online students. So we're going to go through stuff. I don't know if they're going to hear me well or not, but I forgot to get a camera for today to record for them, so we'll do it this way. So we have 3 chapters, right, that we're looking at to review for the next test, which is on Thursday. You guys all ready for that?
Yeah.
Yeah?
Test is in Tuesday. It's my birthday, it actually literally is. This is great.
So yes,
There's 3 of us that won't be here Thursday. There's swimming.
you won't be here.
Yeah. Yeah, I was.
Are you guys,
Yes, sir.
okay.
Take it right now.
Give me, when do you leave?
Like it starts tomorrow.
Wednesday, more often.
Okay. So after class, come up, right? And we will figure something out. How's that? All right? So see me after class, and we'll figure out what we're going to do. Okay. Anybody else that can't be here Thursday? Okay. So, what did you learn from the first test? Just like the problems on the homework. I don't throw curveballs, right? This is going to be, so, what do you need to know how to do, what do you need to study for the test?
The quizzes and the homework.
The quizzes and the homework. What did I tell you last time you needed to study for the test? This is the homework. And you guys didn't take me seriously.
I did.
Okay. All right. So quizzes and homework. So we have, I'm going to assume you got the quizzes. I'm assuming you can handle that since the quizzes tell you what the answer are. Right? So the homework. We have, now, last time, this test is going to be like the last test. There will be 12 multiple choice questions, right? And there will be 4 problems. We're going to have 4 problems like the problems on the homework. Well, on the homework, we had how many problems? 6, I think. Maybe 7. Okay, so 2 here, 2 here, and 2 here. So if you can do all 6 of these problems, right? If you can do all 6 of these problems, then the test should be pretty straightforward. Now,
Make sure I can do all 6 of those problems?
hmm?
Can you make sure I can do all 6 of those problems?
Well, that's what we're doing today. We're going through problems today.
Alright, glad we're on the same page.
All right, we're going through problems today to make sure you can do these problems. If you are struggling with your calculator, please see me. Please, 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 right? Because I would love to help you understand how to operate your calculator. All right, so, chapter 3. All right, working at hockey rink, resurfacing machine breaks down in the middle of the ice. How can you get it moving? How much force do we need to apply to accelerate to 3.7 meters per second in 37 seconds? If the resurfacing machine, this, what are they called?
Zamboni.
Zamboni. If the Zamboni weighs 2365. All right, so. Well, I have a minor issue. And that I can't, oh, there it is. There we go. All right. So we have a force is mass times change in velocity over change in time, over how long you spend changing it, right? Yep, got the T. We had a mass of, what, 2365 kilograms, something like that. We had a change in velocity, which went from 0 to, what was the problem? 0 to 3.7 meters per second. And that happened over a time that was 37 seconds, right? So all we're doing is putting all of this together. So the force is going to be 2365 times 3.7 divided by 37, which is going to be 236.5 newtons. Now, I'm not pushing you guys on units, right? I'm not pushing you guys on units. And in fact, the way we're doing quizzes, you just need the number at the end that goes in, right? You don't have to know the units. So 236.5 newtons. Make sure I put in all the right numbers. 3.7, 37 seconds, 2353. Okay, 2353. Short-term memory. It's the first thing to go. All right. Straightforward enough? Anybody, I mean, this one doesn't have anything difficult in it calculator-wise, right? Where you guys usually struggle with your calculators is when we have, 5 times 10 to the minus 11 or 8 times 10 to the 32 and things like that. All right, pretty clear? Whoop. 3. All right, and remember, you guys have probably noticed by now, whenever you pull up one of the homework problems, you may get different numbers than you did the last time you pulled it up, right? Okay, next problem. All right, so now, we have the mass of the Milky Way is 10 to the 11th times that of the sun, which is, and that the sun is 2.68 times 10 to the 20th meters from the center of the Milky Way. What's the sun orbital speed around the galaxy? And the piece that we're missing here is we need to know the mass of the sun in kilograms. Anybody remember that? Yeah, I'm going to get there the fast way. I'm going to just put in a wrong answer, because that piece was in the details. Okay, so we have the mass of the Milky Way. We need the orbital velocity of the sun around the center of the Milky Way. So, orbital velocity. Orbitalo, yeah, okay. Is it squared? Where's my brain? No, it's not squared. And we use D. All right. So problem 2, we're looking at, this is the equation we have to work with. We know G. And we know G because we're given G, right? G is 6.67 times 10 to the minus 11. And I'm not going to worry about units here. All right, we know M is 10 to the 11th times mass of the sun, right? And this M with a circle and dot in the middle is a symbol for the mass of the sun. And we know that the mass of the sun from the comments, right, 10 to the 11th, is 1.989 times 10 to the 30th. So this ends up being 1.989 times 10 to the 41st. All right, and I'll just put M, right? So now we have the mass, and we're given the distance. Distance was 2.68 times 10 to the 20th meters. Right? Distance 2.68 times 10 to the 20th meters. Now we just have to put it together, right? .67 times 10 minus 11 times 1.989 10 to the 41 divided by 2.68 times 10 to the 20th. All right, so important thing. When you type this into your calculator, depending on how your calculator works, an important thing to make sure you get it right and you don't accidentally do something you don't mean to with your calculator is use parentheses. So you'll want to do something like type 6.67 times 10 to the, times 10 to the minus 11 times 1.989 times 10 to the 41, and then put in your division, and then parentheses again, 2.68 times 10 to the 20. Right? And then you want to do square root of all of that. Now, the reason I suggest that you put square roots around all of this is what I see a lot of you do, is you end up going divide by 2.68, and your calculator goes ahead and does that, right? And then you multiply by 10 to the 20. So what you actually end up doing, the equation you actually end up typing into your calculator is that one, right? And that is not the right equation. That's why I suggest you always use parentheses like this, because by using the parentheses like this on the denominator, you force it into the correct equation. Does that make sense? So, do not do. All right. Everybody caught up on that?
Make sure we put the square root first and then the parentheses and then amount.
That kind of depends on how your
Calculator.
calculator works, and this would need parentheses around the whole thing, right? My calculator, you hit square root last. Some calculators, you hit square root first and then put parentheses around everything, right? And that, so that depends very much on your calculator, yeah. My calculator, it's, all right, here's what I want you to do, that number. And most calculators that you guys have is do this to what follows. Make sense?
And the answer to that would be,
Oh. What would the answer to this be? Let's find out. $222,000 meters per second. Hmm. Can you guys feel that we're moving that fast? Never noticed? It's pretty fast. We're booking along through the universe. All right. Ready for the next one? So, problem 1 of chapter 4. Remote-controlled spacecraft on Mars. Mars is completely inhabited by robots at this point. We put them all there, completely inhabited by robots. How long will it take for the craft to respond to your command if Mars is this far away from Earth and the speed of light is this speed, right? And so in problem 1, what we're looking at is velocity is distance over time. Or in this case, we have the velocity, we have the distance, we want the time. The time is the distance divided by the velocity. The distance we're given is 1,4, let's see if I can copy all of that. All right, this is the distance we're given. The velocity we're given, which is the velocity of light, which light's feeling a little peaked and not moving very fast today, but all right. And so we're after how long does it take? Well, we know how far we have to go. 1,973,7,828 kilometers divided by 298,771. Put parentheses around this, 298,771 kilometers per second. All right? And this is going to give us how many seconds it takes for light to get there. Divided by 298,771. So 501 seconds. You guys see the movie Martian? The Martian? You guys have not seen the movie The Martian? Okay. Yeah. They put these delays in there. If you've ever talked to someone who's around the other side of the world via satellite rather than landline, landline is a little faster because it's a shorter path. If you do it via satellite, it's a longer path, and you'll actually notice a delay. There can be a 3 or 4 second delay. This is a much longer delay, 501 seconds.
8 minutes.
What's that?
8 minutes.
8 minutes. Yep. 8 minutes. And that depends on where Mars is. If Mars is on the opposite side of the sun from us, It's much longer. If Mars is on the same side of the sun as us, it's about like this. This is why the robots, this is why we have to send robots, not remote controlled vehicles, to Mars. Right? We have to be able to program the robot and let it go about its task, doing what it's supposed to do, because we don't have direct control over it. We are 8 minutes away from telling it something to do. Now think about this. Not only is that 8 minutes for us to say, hey, do this, it takes another 8 minutes for whatever it did to get back to us. So it's 16 minutes from when you say do this to when you know whether or not it happened or not. All right, straightforward enough? Okay. Okay.
Does anyone know that on the sheet?
All the way in the back. See if I can find. Oh. So where is this relevant? Well, where's the, no, that's not what I was looking for. See if this is the right website. Nope. I was hoping to very quickly find. So this is a very real problem here. It's not the one I was looking for, but this website is telling us how far the probe Voyager 1 is from the sun, right? In kilometers. So it is much further out than Mars. It takes a long time. In fact, if we sent a signal today to Voyager and said, hey, take a picture, right? And all it had to do was say, yeah, I did it, or no, I didn't. We would not know until sometime Thursday whether or not it took a picture. Right? It would be sometime Thursday before Voyager got back to us saying, yep, I did it. That's how far away Voyager is, even at the speed of light. Right? All right. Next. Problem 2 in chapter 4 is Wayne's law. And it's really simple. The temperature of a star, or for that matter, any object, is 2.96 times 10 to the 6 divided by the peak wavelength that we're getting from that star. Right? So temperature is in peak wavelength in nanometers. So the question is, what is the temperature of a star that radiates, light bulb that radiates most strongly at 3126 nanometers? All right. So, All right? We start with Wayne's Law, 2.9 times 10 to the 6 divided by lambda max. And we only have one thing to worry about in this problem, which is lambda max, which is 3126 nanometers. So, temperature we're looking at is 2.9 times 10 to the 6th divided by 3126, all right, equals 2.9 times 10 to the 6th divided by 3126, so 927 Kelvin.
I got 946.
You got 946? Sure you did 2.9 times 10 to the 6?
I got it.
Okay. A typo somewhere. Yeah. Okay. Those were easy enough, right? Chapter 5. Compare the light gathering power of a telescope that's 11.6 centimeters in diameter to that of the human eye, which is 0.5 centimeters in diameter. All right, so the light gathering power goes as diameter squared. So what we're really comparing is the diameter squared of the telescope to the diameter squared of the eye. So our telescope 11.6 centimeters, eye is 0.5 centimeters. Right? And so we're after how do we compare, basically, how do we compare a large pizza to a small pizza, right? Or a large pizza to a personal pizza, that's what we're comparing. How much bigger is the large pizza than the personal pizza? We have to take the diameter squared divided by the diameter squared. So in this case, we're looking at, we have 11.6 squared divided by 0.5 squared. So 538 times larger. Right? That's a lot larger. That's why, because it goes as diameter squared, that's why the medium pizza is actually a good bit smaller than the large pizza. Okay? Everybody get that one? No? Oh. Okay. All right. In arc seconds, what is the smallest crater the unaided human eye can resolve on the moon? We're going to take the diameter of the pupil to be 0.5 centimeters again, and the wavelength to be 242. All right, I didn't give you the equations up front on this one, so we'll go ahead and grab the equations. All right, so the fundamental thing is that the diameter we're interested in is 0.02 lambda divided by the arc length in arc seconds. Now, we just have to solve this equation for the arc length, alpha, because we already have the diameter of the eye, right? And we already have the wavelength we're after, 542 nanometers. So, problem 2, the smallest wavelength we can see is 0.02 lambda divided by the diameter of the eye. I mean, the smallest angle we can see, 0.02 lambda divided by the diameter of the eye. Now, this is due to something called diffraction, right? Diffraction is the scattering of light as it goes through an aperture. So your pupil is an aperture, and as light comes through it, it scatters. It doesn't cast a perfect shadow. It doesn't come straight through. It actually has a little bit of a fringe around it. So let's look at what this would be. Alpha 0.02 times 542 divided by 0.5, right? 0.02 times 542 divided by 0.5, and we get 21.7 or 21.7 arc seconds. All right? Bless you. See if I can do something real quick. I'm going to try and show you guys real quick some diffraction. And we may end up having to turn the lights out to do this, but let's take a look. All right. Everybody got this last one? We're all cool on that? Any questions on any of the problems?
And where do I write it all out right, and then type in our calculator on, do I get partial credit?
Unfortunately, because we have an online section that has to go through the same thing, and they don't get partial credit, I can't give you guys partial credit, right? So I'm really looking for, now, you don't have to get exactly the numbers I get, right? You have to be within a certain range around the number I get. So it doesn't have to be exact. All right, let me show